Swayam Prabha. Digital India. Educated India.
Hello and welcome to Lecture 16 of Computer Aided Engineering Design. We will continue with our discussion on the design of Bezier segments and curves. Let me warn you beforehand that the mathematics is going to get quite involved from now on. We'll start with Bezier segments first. We have informally introduced what Bezier segments are, but formally this is what the definition is. The position vector of a point on the Bezier curve is given by summation I going from 0 to n combination I times 1 minus u raised to n minus I times u raised to I times pi. This expression here is our Bernstein polynomial of degree n. U is our parameter and p sub I are the design points specified by you as a designer. This is equal to summation I going from 0 to n b sub I n of u times pi, the ith Bernstein polynomial. Parameter u varies between 0 and 1. We have seen this before when we are discussing Ferguson curves and also Bezier curves, that individual segments, they need to be of lower order, preferably cubic. Once again, to remind us, we need this to minimize oscillations in a segment. If a Bezier segment is cubic, it will be needing 4 data points, P0, P1, P2, and P3. You can call them as design points or control points. We have seen before that are individual terms emanating from the binomial expansion of 1 minus u plus u raised to n. You would know the expressions for the. I'm going to be using those expressions directly. The position vector Ru is given as 1 minus u raised to 3 times p0 plus 3 times u times 1 minus u squared times p1 plus 3 u squared times 1 minus u times p2 plus u cubed times p3. I can expand these expressions and I can rearrange this equation so that I can get the coefficients of u cubed, u squared, u, and a constant 1. These coefficients are minus p0 plus 3p1 minus 3p2 plus p3, 3p0 minus 6p1 plus 3p2, minus 3p0 plus 3p1 and p0. And like we did this in case of a cubic Ferguson curve, we are going to be representing this expression in the matrix form or the compact form. This is a 1 by 4 matrix containing the terms of u, u cubed, u squared, u and 1. This is a 4 by 4 constant matrix with elements in the first row as minus 1, 3, minus 3 and 1. In the second row, 3, minus 6, 3 and 0. For the third row, we have minus 3, 3, 0, 0 and 1, 0, 0, 0. This here is a 4 by 3 geometric matrix P0, P1, P2, and P3, constituted of the data points that a designer has specified. This is a very similar expression that we see in case of cubic Ferguson curves. In short, this 1 by 4 matrix is represented by capital U in bold. This 4 by 4 matrix is represented by M sub B. B refers to the Bezier segment, and G is this geometric matrix. To reiterate, U is a 1 by 4 row matrix. M sub B is a 4 by 4 Bezier matrix, and G is a 4 by 3 geometric matrix. Recall that in case of cubic Ferguson curves, this geometric matrix had information pertaining to the two endpoints and the two end slopes. Let's take a look at an example. Let's say we are given control points P0 by coordinates 1, 0, P1 by 4 and minus 5, P2 by 6 and minus 6, and P3 by 10 and 2. Let's compute the Bezier curve. And further, let's observe the shape change when point P2 is moved from its previous location 6 minus 6 to a new location 7 and 8. And following that, when point P1 is moved from its location 4 minus 5 to a new location 9 minus 6. The position vector is given by XU. This is a 1 by 4 row matrix in terms of U. This is a 4 by 4 Bezier matrix, and this is where we specify the geometry. 1, 0 for point P1, 4 minus 5 for P2, 6 minus 6 for P3, and 10, 2 for P4. Working out the algebra is not very difficult here, so I'll just give you the results. The x component is given by 3u cubed minus 3u squared plus 9u plus 1, and the y component is given by 5u cubed plus 12u squared minus 15u. Let's look at the Bezier curve graphically. This is the original set of control points. Let's join them together to form a control polyline. This is how the first Bezier curve looks. Now let's move this point to its new location. This is the resulting polyline for which the Bezier curve is given by that in red. Let's now move this point to its new respective location. The resulting polyline and the resulting Bezier curve. Or maybe I should say these are all Bezier segments at degree 3. What do we observe? Let me go back. Notice the shape of the blue segment, and then the red segment, and then the green segment. Question: is the change in shape local or global? You have it right. It is, in fact, global. A relocation of any data point changes the shape of the entire segment. We'll worry about that a little later. Some properties of Bezier segments. We have discussed properties of Bernstein polynomials before. A lot of the properties of Bezier segments can be directly derived from those of Bernstein polynomials. Let's look at some of them. First, the endpoints of a Bezier segment. At parameter value u equals 0, the first Bernstein polynomial is 1, while all the other Bernstein polynomials are 0, which would mean that p sub 0, the first design point, would be one of the endpoints of a Bezier segment. Now, this is true for any n degree Bezier curve. For parameter value u equals 1, the last Bernstein polynomial is 1, while all other polynomials are 0. This would mean that the last design point, p sub n, is another endpoint on the segment. End slopes or end tangents. These are given by the vectors p1 minus p0 and pn minus pn minus 1. These vectors would correspond to the first segment of the control polyline and the last segment of the control polyline. If you recall, we had computed the first derivative of Bernstein polynomials a while ago. If we compute this first derivative of a Bezier curve, you can find that this is given by summation j equals 0 to n p sub j times the first derivative of the Bernstein polynomial, the jth Bernstein polynomial of degree n, that is equal to j going from 0 to n p sub j n times the j minus 1th Bernstein polynomial of degree n minus 1 minus the jth polynomial of degree n minus 1. We can bring in this summation sign inside. Once we do that, this expression here is equal to n times summation j going from 0 to n minus 1 b j minus 1 n minus 1, a function of u, minus summation j equals 0 to n minus 1 pj b sub j n minus 1, again a function of u, and that is equal to n times summation j going from 0 to n minus 1 pj plus 1 b j n minus 1 minus j going from 0 to n minus 1 pj b sub j super n minus 1. What have we done? We have simply raised the index of this term here, and accordingly we have changed the limits here as well. We have the convention that b sub minus 1 super n minus 1 of u is 0. This is an exercise for you to determine why this is so. Once we use this information here, the first derivative of a Bezier curve would become n times summation j going from 0 to n minus 1 p j plus 1 minus, within parenthesis, times the jth Bernstein polynomial, or degree n minus 1. Now, for u equals 0, all the other Bernstein polynomials except for the first one will be 0. And for u equals 1, all but the last one will be 0. We use this observation to find that the first derivative of a Bezier curve at u equals 0 is given by n times p1 minus p0, and the slope of the curve or of the segment at u equals 1 is given by n times pn minus 1. We have just shown that this statement is true. Next, geometry invariance. From partition of unity property of the Bernstein polynomials, the shape of the curve is invariant under rotation and translation of the coordinate frame. I recommend that you revisit the discussion on barycentric coordinates and affine combination. There we had stated that when the weights in the combination sum to 1, the shape of the curve does not change when the coordinate system is rotated or translated. Let me explain this concept on board. Let me draw the control polyline of any generic Bezier curve. And let me also sketch roughly the Bezier curve. You have seen that the segment will start from this point and it will end at this point. We have also seen that the first segment of the control polyline and the last segment of the control polyline will be tangent to the Bezier segment. This is how a typical Bezier segment will look. We'll roughly discuss what the intermediate shape of a Bezier segment will look like, but that is for later. For now, the geometry invariance property states that no matter what coordinate system I use to express this segment, whether this or whether this or whether this one here, no matter what coordinate system I use to express the shape of a Bezier segment, this shape will remain unchanged. And this is due to the fact that the Bernstein polynomials, they all sum to 1, which would preserve the affine combination. This is an important property, the convex hull property. The barycentric nature of Bernstein polynomials ensures that the Bezier segment lies within the convex hull of the control points. For example, let this be a generic control polyline, and correspondingly, let this be the Bezier segment. The question: how would you determine the convex hull for a set of points? I'll explain that a little later, But for now, let the convex hull be given by this shaded area. For any value of parameter u, the entire curve will always lie within the convex hull of the given design points or data points. Let me explain how to draw the convex hull for a given set of data points. I start with first specifying the design points. Let's say this is my control polyline. Let me close the loop here. And let me pose this question to you. Is this the convex hull for these data points specified? The answer to my question is no. Why is that so? By definition of a convex hull, if I choose any 2 points P1 and P2 within the hull, and if I draw a straight line, then all the points in the straight line, or in other words, the entire straight line, should lie within the convex hull. Now let me choose 2 points here and here, and let me join them using a line segment. You would notice that a part of this line is outside the hull. Let me choose another set of intermediate points, and let me join them again using a line segment. Once again, this portion of the segment is outside the hull. The actual convex hull, which is unique for a given set of data points, can be sketched like so. You can use this definition and verify that for any 2 points within this hull, the corresponding line segment joining the 2 points will always lie within the convex hull. Note that this convex hull is unique for given data points. Going further into investigating the properties of Bezier segments. Variation diminishing property. Here we see or we observe how we can roughly depict the shape of a Bezier segment. For a planar Bezier segment, it can be verified geometrically that no straight line on that plane intersects with the segment more times than it does with the corresponding control polygon. Don't worry about the grammar of this long statement. I'll explain this to you with an example here. Let me start with a generic control polyline again, and let me draw the corresponding Bezier segment. This is a 2-dimensional example. An extension of this example in 3D would always also work. Now let me first draw a line segment that intersects with the control polyline and the Bezier segment. In other words, this line segment is going to be cutting both the control polyline and the Bezier segment. Let us first plot the intersection points between this line and the control polyline. These are shown using blue circles. Let us now observe the intersection points between the Bezier segment and this intersecting line. Those are shown using red circles. Once again, the blue circles are the intersection points between the control polyline and the intersecting line, and the red circles are the intersection points between the Bezier segment and this line segment here. What do we notice? We notice in this example that the intersection points in both cases in number are the same. 3 blue circles and the 3 red circles. What this property says is the following. It will never ever happen that the number of red circles will be more than the number of blue circles. In other words, the number of intersection points between the segment and this line will never be more than the number of intersection points between the control polyline and the intersecting line. This would physically mean that the shape of this Bezier segment will be no more complex than the shape of the control polyline itself. In other words, this control polyline roughly depicts or approximates the shape of the Bezier curve. I specify the data points again. And I sketch the control polyline. Let me sketch an arbitrary Bezier segment, starting from the first point, ending at the last point. Once again, the first and the last segments of the control polyline are tangents to the Bezier curve. Let's assume for now that the shape of the Bezier curve looks like this. Let me draw an intersecting line. You would notice that the number of intersection points between the Bezier segment and this line would be a lot more than the number of intersection points between this control polyline and this intersecting segment. What the property says is that such a scenario is never possible. In fact, the actual Bezier segment can be roughly sketched like so. To re-emphasize, this is not a possibility. And this is an approximate depiction. In a three-dimensional case, for a spatial Bezier curve, the property holds for a plane intersecting a three-dimensional Bezier segment and its control polygon. This is what I have said before, that the shape of a Bezier segment is no more complex than its control polygon, and it's roughly predictable by the latter. Continuing with the properties, no local control. The shape of a Bezier segment changes globally for any data point moving to a new location. Let's try to analyze this property algebraically. Let a control point P sub k be relocated along a specified vector v. So the new Bezier segment R super new will be given by summation I going from 0 to n and I not equal to k. The terms in the summation are the ith Bernstein polynomial of degree n times the control points pi plus the kth Bernstein polynomial of degree n times the new relocated control point p sub k plus v. What we can do is we can bring this term back into this summation to get I going from 0 to n in summation terms b sub I super n times the design points plus b sub k super n times the vector v. This is equal to the original Bezier segment plus an additional term b sub k super n, a function of u, times the vector v. We see that every point on the old Bezier segment Ru gets translated by the term b sub k super n times v. So note that this is actually a vector. So individual components x, y, and z of the Bezier segment will get translated. Once again, every point on the old Bezier segment gets translated by the term b sub k super n times v, implying that the shape of the entire segment gets changed. Let's look at some derivatives of Bezier segments. The first derivative, total Ru over total u, is given by summation I going from 0 to n times the I minus 1th Bernstein polynomial of degree n minus 1 minus the ith Bernstein polynomial of degree n minus 1 times the design point pi. This term here is nothing but the first derivative of Bernstein polynomial b I super n. We can take this term n out and expand this expression to get n summation I going from 0 to n b I minus 1 super n minus 1 times pi minus n times summation I going from 0 to n b sub I super n minus 1 times pi. What we do is we write the first term of this expression separately, and we write the last term of this expression again separately. So this is the first term in this expression or in this summation, and this is the last term in this summation, and these are the rest of the terms in this expression. This is n times b minus 1 raised to n minus 1 times p0 plus n times summation I going from 1 to n b I minus 1 n minus 1 times pi minus n times I going from 0 to n minus 1 b sub I super n minus 1 pi minus n times b sub n super n minus 1 times pn. By convention, b minus 1 n minus 1 is 0. Likewise, b sub n super n minus 1 is 0. This is an exercise for you to find why this is so. We are left with these two terms, and we combine them together to get n times summation I going from 0 to n minus 1, the ith Bernstein polynomial or degree n minus 1 times, within parentheses, the I plus 1th design point minus the ith design point. What do we see? If you try to compare this expression with an nth degree Bezier segment, we observe that this is very similar to that. The only difference is there we had the position vectors of the design points, but here we have free vectors. The degree of this curve will be n minus 1. So, a Bezier segment of degree n minus 1 but with free vectors is obtained, and this segment is called a hodograph. How would a hodograph look? Let's consider a cubic Bezier segment. Notice that these vectors are free vectors. This is p1 minus p0, p2 minus p1, and p3 minus p2. This would mean that I can move around these vectors any way I want. This curve is a Bezier curve. Let's move these free vectors at will. I show here only one of the cases, rather one of the many cases. I coincide the tails of all these free vectors at the origin of the coordinate system. The tips here will lie on this green curve, which is the hodograph. In any other case, I could have moved these three vectors anywhere else I would have wanted. What am I suggesting? That this green curve, the hodograph, is not unique. Let's look at some higher order derivatives of Bezier segments. d2r over du squared is given by n times summation I going from 0 to n d over du of b sub I super n minus 1 times pi plus 1 minus pi. This expression here relates to the first derivative of the Bezier segment. I can work the algebra in detail. Let me not worry about the intermediate steps, but I'll have them for you on the slide just in case you want to take a look at leisure later on. A note here, this term here will become 0 because there is a -1 index here for the Bernstein polynomial. And likewise, this term here again will become 0 because the index over here is larger than the degree of the Bernstein polynomial here. By convention, we make these Bernstein polynomials 0. Of course, there is a reason, and I have asked you to find out this reason yourself. Likewise here, the index is larger than the degree of the Bernstein polynomial. And so is the case here. Anyhow, this is one of the final results. N times n minus 1 summation I going from 1 to n minus 1, the I minus 1th Bernstein polynomial of degree n minus 2 times I plus 1th design point minus the ith design point minus n times n minus 1 summation I going from 0 to n minus 2, the ith Bernstein polynomial of degree n minus 2 times pi plus 1 minus pi. We rearrange this expression to get the final result as n times n minus 1 summation I going from 0 to n minus 2, the ith Bernstein polynomial of degree n minus 2 now times pi plus 2 minus 2 pi plus 1 plus pi. If you carefully observe, this is actually pi plus 2 minus pi plus 1 minus of pi plus 1 minus pi within parentheses. Likewise, we can compute the third derivative of a Bezier segment. That is given by n times n minus 1 times n minus 2 summation I going from 0 to n minus 3 b sub I super n minus 3 times pi plus 3 minus 3 pi plus 2 plus 3 pi plus 1 minus pi. The algebra should not be very difficult. It should be straightforward. You should be able to compute and verify this result. We can generalize these results. We can say that the kth derivative of a Bezier segment is given by n times n minus 1 times n minus 2 up till n minus k plus 1 summation I going from 0 to n minus k. What do you expect now? You're right. You're expecting the ith Bernstein polynomial of degree n minus k. Observe right here. Ith Bernstein polynomial of degree n minus 3 for the third derivative. What I've done is I have generalized these expressions by d sub I super k. If I start with d sub I super 0 as my original control points p sub I, then I can have a recursive relation given by d sub I super j is equal to d I plus 1 j minus 1 minus d I j minus 1. J would represent the derivative. For example, j is equal to 1 will give the first derivative, j is equal to 2 will give the second derivative, and so on and so forth. that goes from 0 to n minus j. For example, di1 is equal to di plus 1 0 minus di 0. This is pi plus 1, this is pi. di2 is equal to di plus 1 1 minus di1. What is di plus 1 1? Use a similar expression here. This is pi plus 2 minus pi plus 1 minus di1. Get this expression directly over here. Pi plus 1 minus pi. A little rearrangement will give you pi plus 2 minus 2 times pi plus 1 plus pi. Likewise, what is d sub I super 3? To get d sub I plus 1 super 2, all we need to do is raise the index of this by 1. That's correct. We'll get pi plus 3 minus 2 pi plus 2 plus pi plus 1. We already have the expression for this, di2 right here. This is pi plus 2 minus 2 pi plus 1 plus pi. Rearrange to get pi plus 3 minus 3 times pi plus 2 plus 3 times pi plus 1 minus pi, which is the expression right here.